design injection level into the node. The head end guy at the receiver takes a look at the optical power that he's getting, right? Because these receivers, optical receivers in the head end, have a sweet spot at the input, just like RF amplifiers do, and he attenuates that optical input so that the optical power level falls within that window. And then the head end guy then sets the RF test point levels out of the receiver. Those steps are real general. Again, you should follow your vendor's specification. There we go. Okay, so in other words, if you inject that plus 20 or whatever your reverse design level is into the node, you go backwards through the optical part, and then the head end guy is going to set all these nodes up so that they're all the same, right? And then you're going to feed that into a reverse combiner, and then through the reverse combiner into the input of the 5510. And notice that pad of the input, I padded that down so that I have 0 dBmV at the input there. Why did I do that? Number one, that's the sweet spot of the 5510. And number two, I want to have the same levels at the input to the 5510 as I have at the CMTS, right? If I can. So make sure that when you send these carrier levels back, that you pad the input of that 5510 so that it has 0 dBmV. And when you look at your node every morning, when you're establishing your reference, you're going to look at that screen and look for that telemetry carrier level and make sure it's the same. Because if a head end guy changed anything in here since the day before, you're going to see it in your sweep trace or your telemetry level. Come on. There we go. Okay, also, we have to make sure that we minimize the noise on a return path, because you can see I've got a noise level of minus 35 up there with just 4 nodes on it, right? Every time I double the number of nodes, my noise gets worse by 3 dB, right? So if I have 35 and 35 and I combine those two, my noise is going to be 32. If I combine those two with the other two, my noise is going to be 28 dB, okay? Carrier to noise. And by the way, you have to have 20 dB carrier to noise on the telemetry frequency at the input to the 5510 in order for it to work. So you can see the more nodes you combine at the input to that, the more noise you're going to have and the less reliable your sweep system is going to be. But that doesn't mean that you can't combine 8 or 16 nodes, because a lot of times that just works just fine. So let's talk about return sweep here. If we can get it to go the way I want it. Okay, so you're going to inject the raw sweep with that known input to your return amp or your node. You're going to check for that telemetry carrier level back at the 5510 on your screen, and if anything has changed from the night before, you got to figure out what it was. Did somebody change the return combination into head end? Did he put in a splitter so we had a test point? What was it, right? So check for that telemetry carrier every morning. It should be 0 or close to it. New reference every day, just like before. Store the reference and then change it to 2 dB per division. Sweep all the active test points and store the traces and send them upstream. We already talked about this. This is what the field unit is going to put out, just these sweep points, right? And again, you can put them in between the carriers so that you get resolution all the way across. so that you get resolution all the way across the frequency. Okay, so there's a couple of things you got to know about return sweep just before you start. First of all, you got to know your equipment. An Aris amplifier and a Cisco amplifier essentially do the same thing, but there are different things within each amplifier. For example, test points. Does the test point cover one port or two ports? Is it bidirectional or is it resistive, which means, or is it directional? Bidirectional or directional, right? You got to know that. Is the test point in between the diplexer or is it outside the diplexers? Okay, some amplifiers have test points in between the diplexers, and if you have a test point in between the diplexer, you can't use that for an injection point, right? So you got to know your equipment, and you also have to know your test equipment too. Our sweep system works the same as a KLN sweep system, but there's differences, right? You got to know your equipment. You also have to know your reverse sweep input levels. That's something that's system specific. I can't tell you what that is, okay? It's every bit the same as a downstream design levels, right? It's based on the system. So determine input reference points, and I don't know anybody that uses anything but input to the diplexer anymore. Optimize the return lasers first, and then sweep the coax part of the plant. Okay, and that's know your test equipment. Okay. I don't understand what this is doing here. There we go. Okay, so there's a typical amplifier block diagram, and you can see that this test point here is for both, I'm sorry, this is for the downstream, but you can see that this test point here for the return covers both nodes. So if you put your meter there and looking for ingress, for example, how are you going to know which port it's coming off of? You don't, okay? So all I'm trying to point out here is you got to know your amplifiers, because hopefully here's another different one. I don't know why it always goes backwards first. There's a different amplifier. And you can see on this amplifier, I've got a test point for every port, right? All I'm saying is you got to know your amplifiers and how they're constructed and their block diagrams. And if you don't know the block diagram of the amplifier, you need to get it. The injection levels are usually at the input to the diplexers. Used to be in the old days, some people used to balance for the input to the hybrid. I don't know anybody that does that anymore. I guess we're going backwards again. Even though I'm pressing the same button. There we go. Okay, so how does reverse sweep? I sort of talked about this before. The field unit in the downstream listens for that return telemetry carrier, the downstream return telemetry carrier. And it's just like a modem. Once it gets that downstream telemetry carrier, it locks on it, and the downstream telemetry carrier has upstream transmit instructions, right? So it listens to the downstream, it gets the sweep table from the transmitter in the head end, and then it starts to inject sweep, okay? One carrier at a time, but it's on, off, it's on, off, moves up a little bit, turns on, turns off, moves up a little bit, turns on, turns off. Only injects one carrier at a time, but it injects them so fast across the spectrum that to us carbon-based units, it looks like a sweep trace, right? Okay, so the meter injects the sweep points into the system, goes backwards through our optics, goes into the head-end transmitter. The head-end transmitter looks at its own sweep trace, digitizes it, puts it on a telemetry carrier, and the telemetry carrier carries the sweep trace back out to the field unit so that you can see. Now, if I inject 20 at the node, okay, and I establish that a reference of 0 dBmV back at the head end, right? And I go to the next amp and cascade and I inject 20 there, and as long as I have that same level back here at the head end, what does that mean? It means I have 20 at the input to the node. And if I go out here and inject that same level and get a flat sweep trace, it means I have 20 at the input to this amp and 20 at input to that amp. Okay? So that's how return sweep works. Okay, so here's a raw return sweep trace, for example. I'm injecting at a particular level, that return sweep level, and again, there's my telemetry level right there at the head end. And notice that my sweep trace is at about -2 or so. So now what am I going to do? I'm going to store that reference. Come on. I'm going to store that reference and I get a flat line just like I did in the forward path, right? And as long as you inject those same levels at each amplifier, at each return amplifier, and you set that sweep trace on the 0 line, your input levels to the next amp in cascade in the return path are going to be correct. Okay, and here's what a raw sweep trace looks like on an ONX. And there's the reference trace on an ONX. And the ONX in the return path also has alignment tabs so that you can see, number one, how much carrier level you're injecting and how much carrier level is at the head end and what's the loss in between. Okay, and like I said, we're in the return path. Now we're going to set all the output levels so that I have +20 at the input to each return amp. And you can see these output levels are different from this amp and this amp so that I get +20 at the input here. Still squirrely. Okay. All right, so what are we finding? I stole this from Todd Zuter, so if you've seen it before, that's why. So in any event, most upstream events are at the low end of the spectrum, low end of the return spectrum, and when DOCSIS breaks its bond in the return path, it's usually on the low end. In other words, the lower frequencies break bond with the higher ones. And let's take a look at that. And I think you guys may have seen this slide before, and some of it went away, but oh, here we go. So here we go at the modem here. You can see that at the end of this network here, this modem is not transmitting those carrier levels. Come on. In any event, if we have constant flat inputs all the way back, okay, what happens is the modems further out in the system have a lower transmit level on the low frequencies than they do on the high frequencies. So how can we combat that? Well, if we put a little equalization in the node, what happens is that has the effect of evening out those two carrier levels because we have cable loss here and cable loss in the head end. That's what caused the problem in the first place, so we're going to add a little equalization. And as we go out to 85 megahertz and beyond, we're going to have equalization anyway in the return path. And if that didn't convince you, the modems being the same level, that picture should. That picture is before and after adding equalization to the node.